So, welcome to this lecture. We have been discussing with the Hopkinson test and the connection I will better draw once again very quickly. So, one machine you connect it as a shunt machine like this, and another machine whose armature is this and whose field is this. This field and here is your supply V rated voltage, and this one you connect it here, and so field winding of both the machines are separately excited from this voltage straight. This current is IFG and this current is IFM, that was there, and these machines, these two armatures are eventually paralleled. Some conditions to be fulfilled that I told you, it is like this connected, and these two motors are mechanically coupled. So, they cannot but run at the same speed n. Okay. And it's adjusts the field currents of this machine such that here is your RAG and the polarity of the voltage should be like this, this is EG, and similarly here it is RAM and polarity, and this is the back EMF of the motor EM. And I will make EG greater than EM, so that current will flow. This is the armature current of the generator, as you can see. This is the armature current of the motor, and this is the current drawn from the supply. Now, obviously, this total current, total power drawn from the supply, power, this we did last day only, power drawn from the supply is equal to V into IL. Okay. And from this power, if you total rotational loss of both the machines is suppose W naught is equal to input power drawn from the supply, and then go on subtracting the losses, that is field copper loss, we did it last time, minus V into IFG, field copper loss of the generator, armature copper loss IAM square RAM minus IAG square into RAG. Then we say that okay, this we have estimated the total copper. So, from the supply, the power drawn, whatever power it draws, must be all the losses. That is what I am telling. Although there is armature current now, sufficient armature current, there is sufficient generator current, but power drawn from the supply will be only all the losses taking place in the machine. Let us go ahead. So, this is the rotational loss. Now, suppose I want to, so this generator is, armature current is no longer no load current, it is I can adjust the field resistance of the generator and motor such that EM is less than EG, and current directions will be like this. Therefore, I can now calculate the efficiency of this machine and that machine. See, I told you these two machines are similar or identical. In that case, RAG and RAM will be equal, but I have taken a most general case, even if it is little difference, let it be like that. So, I will say, see how I am writing. I will write straight away the efficiency of the motor to be. For a motor, which thing is easy to calculate? The input power is very easy to calculate. You calculate input power, output by input is the efficiency. So, what is the input power to this motor? It is, input will come in the denominator. So, it is V into I Fm field copper loss plus V into I am. This will be the total input power to this motor. Got the point? Input power to the motor. And what will be the output power? Output power will be V into IFM input plus the losses. Minus the losses, minus input power minus the losses. What are the losses? Field copper loss, V into IFM, motor losses minus IAM squared into RAM, copper loss of the armature, minus the rotational loss, which is W naught by 2. So, we after this we say that rotational loss of each machine will be approximately W naught by 2. W naught I estimated rotational loss of both the machines, because there will be eddy current loss in the armature, frictional loss on the shaft of the machines. Why I am saying it is approximate? Simply because, see, although this experiment is nice, but you see the field current of the machine which is acting as a generator is greater than the field current of the motor. Therefore, flux level in the both the machines are not same, although speed is same. But anyway, this is how I am estimating. So, this will be the efficiency of the motor, that is all. Similarly, so this is efficiency of the motor. Similarly, I will be able to write down the efficiency of the generator. In case of generator, it is easier to calculate the output first. For example, what is the output power of the generator? This voltage is V. So, this is also V, is not V. V into IAG is the output power. This is the output power, output of the generator. And to this output power, you go on adding the losses to get the input power of the generator. So, output VA IAG, VIG I wrote or IAG, I am sorry, VIAG is the output power. So, output plus the losses. What are the losses? Field copper loss VIFG plus armature copper loss I AG square into RAG plus the rotational loss W naught by 2. This will be the efficiency of the generator. So, you see, in this experiment compared with Swinburne test, here you will be able to load the machines to their rated current, but supply will never know. Supply will only supply the losses. So, current drawn from the supply is not large, little current IL, which comprises of the copper loss of these two field coils and armature copper losses and rotational loss, that is all. Now, it may look surprising why it is happening like that, but still I am telling the output of the generator V into IAG will be large. Input to the motor is large V into IAM, IAM is no load current, it is IAM. The answer to that is this one, that what is happening, these two machines are coupled, is not? Acha, motor, this is N speed, and electromagnetic torque developed by the machine will be same direction as that of that, is not? Similarly, generator direction of rotation is same. N, but electromagnetic torque developed by the generator will be in the opposite direction, TEG. See, for this motor does not know, it will only see on the shaft there is an opposing torque, that is why it is behaving like a motor. It will draw more current, whether this torque has come by your direct belt loading, the thing I discussed, that it cannot distinguish. It will see, okay, on the shaft there is now some opposing torque, draw more current. Similarly, for the generator mode, this electromagnetic torque produced by the motor is in the same direction. So, this is the prime mover torque of the generator. TEM is nothing but the prime mover torque of the generator. TEM is provided by whom? By the motor. Load torque is provided by whom? Is by the electromagnetic torque of the generator. Therefore, the motor will always see, okay, this generator is nothing but mechanical load to me. Similarly, generator will see, okay, this motor is nothing but the prime mover to me. Got the point? Therefore, this motor will run this generator as a prime mover. Similarly, this generator will give supply to the motor. Therefore, this is how they will manage to survive with sufficiently large armature currents. But our purpose is to see that they are carrying rated currents, then calculate efficiency. Rated current means if it is 20 ampere rated current, you can adjust the field current so that these currents are really 20 ampere. So, armature currents will be rated current, but the current drawn from the source will be only very little. That is the advantage. So, this is how elaborately you can calculate. But only thing I must tell that this assumption that the rotational losses are same is not exactly correct. But anyway, that will cause a little error. At least you get this performance of the machine, temperature rise, etc. Will be can be well documented by really passing the rated currents to the machine armatures. That is the greatest advantage. But another thing is you must have two machines together which are mechanically coupled, otherwise you cannot do it. So, this is how it can be done. Sometimes what people say, so in this experiment you must understand that if you connect, you have to connect several meters, suppose you connect an ammeter here, this ammeter, connect an ammeter there. This records field currents of the generator, connect a voltmeter there to record the voltmeter. Those meters connections I have not shown. You can connect a meter here to record the field current of the motor, this, that. But the interesting thing is that when the setup is running with all meters showing, I can conclude that from the readings of the motor and generator field current, whichever field winding is carrying higher current, that will be acting as a generator. See, after you have paralleled them, you can do it like this. I will reduce the field current, increase the field current of this one. Then this fellow will start acting as a generator, and this fellow will act as a motor. Got the point? It is the fight between EM and EG, who is larger, that will decide whether this fellow is motor or generator. Generally, the field current of the machines whose field current is larger, that will act as a generator, whose field current is small, it will act as a motor. And finally, one thing is I will tell that in this experiment, people say that okay, so motor is driving the generator as a prime mover, and generator will see that it is supplying a load to a motor, like that it is happening. One interesting way for quick calculations, people sometimes use this, that suppose let the efficiency of both the machines are same. Suppose efficiency is because they are similar machine, I assume the efficiency of the machine they are same. Here coming back, suppose the efficiencies are same, then what I am planning to do is this, that what is the output of the generator? Output of the generator is how much? V into IAG. Oh, sorry, somehow this page was this page. Let the efficiencies are same. So, what is the output of the generator? V into IAG, output of the generator. What will be its input? Input must be divided by efficiency are same and equal to eta, suppose. So, this is output of generator, output of generator, that divided by efficiency, this quantity is input to the generator. Is not? This must be the input to the generator. Now, input to the generator is coming from where? Input to the generator is coming from the output of the motor. Okay. So, what is the output of the motor? I want to calculate. What is the input to the motor? Input to the motor is armature, input to the armature is V into IM. That into efficiency, I mean roughly it should be same, or I will say that eta square is equal to I AG by IM, or efficiency of each machine very quickly if you want. Okay, detail actual calculation I do, I can get the correct efficiencies, no doubt about that. But only what I am telling is, if you have connected all the meter readings, you know IFG, you know IAG, you know IAM, suppose you have connected an ammeter here also, then you see the efficiency of each of the machines will be under root approximately the armature current of the generator by armature current of the motor, approximately as a first calculations you can say like that. So, anyway, read about it, particularly the connections is very interesting. Armatures are connected in parallel, field windings are also connected in parallel. So, it will give you a fair idea, it will further strengthen your operations of DC machines, either as a motor or generator, whatever it is, you can do it. In this context, I will just point out one thing, you must have solved problems in the meantime. Suppose you have a machine, okay, you have a which is separately excited. Try to I mean with this you can now say that suppose here is a machine, separately excited machine, okay. You run with a prime mover, then here you will get voltage, is not generated voltage K phi n, prime mover it is driven by. Now, suppose here you have a supply, say V volts, and I have planned to connect this to this supply. So, before connecting, of course, you must connect a, just like Hopkinson test, only thing this is not coming from the armature of another machine. This supply is there, here is a, I am running it as a generator first, adjusting the field current. I will also make this voltage to be plus V, then what will be the voltmeter reading? 0. If it is 220 volt supply, adjust the field current and speed whatever it is, rated speed you are running, adjust the field current, so that this voltage is also 220 volt with this polarity, and connect an ammeter here. And if I now close this switch, what will be the ammeter reading? 0, because the equivalent circuit of this is this one. Here is some generated voltage E g, here is some R A, and here is your supply, is not. And the value of E g depends on this flux or the field current I f. So, I can, if I wish, increase this E g above V. I will increase after connecting, successfully connecting in parallel with this supply, I will play with this field current, I will increase this field current. If I do that, then the current will be like this, separately excited machine, mind you, current will go to the positive terminal of the battery. So, here is a DC bus, DC supply plus minus. Therefore, if you increase the field current, E g will become, E g will win over V, and it will start delivering current in this direction. That is, it will pump power onto the bus. And on the bus, if it is DC bus, you do not worry, there must be load already connected, some other fellows are using that DC supply. Therefore, your generator will deliver power to the bus. What is the DC bus? To where supply is available, fixed voltage, where several other loads are connected. You have now made this DC machine a member of this bus by doing this, ensuring that the voltmeter reading is 0, paralleled it comes like that. If E g is exactly equal to V, then this I will be 0, then this I will be 0 if E g is equal to V. So, this machine is neither acting as a motor nor as a generator, it is just floating in the bus. If you see now this generator, let it contribute some power to the bus where already load is present, some other generators are maintaining those loads. Then what you do? You increase this voltage, then I will be flowing from left to right. Okay? Got the point? Therefore, by adjusting this field current, I can do it like that. What will happen if this prime mover is disconnected? It is connected parallel, separately excited, field is supplied. Suppose because of some reason, it is prime mover means what? Some other engine, it is driving the generator. Suppose the prime mover is detached, then what is going to happen? Then this machine armature is already connected across this supply, field is there is no prime mover. Therefore, it will run as a motor, and obviously, it will draw current from the supply. You may then say it was running as a generator because E g was greater than V, I have disconnected the prime mover, then how it can run as a motor? Still will it not supply power there? Yes, it will for some time it will supply power, but if it supplies power, that opposing torque is present, but there is no prime mover torque. So, speed will fall. So, it will come to such a speed, such that it can draw enough power from this bus, so that it will run as a motor and supply whatever no load power is present. I mean shaft power is present like friction and rotational loss. Got the point? In case of generator, electromagnetic torque and prime mover torque are in the opposite direction. This is prime mover torque for this generator, this is electromagnetic torque. Now, what I am telling, suddenly I say T p m goes disconnected, no prime mover, then what will happen? Electromagnetic torque it was doing, so it will decelerate, speed will fall, E g will fall, so that then V will become greater than E g at some time, and then it will drawing current from the bus. So, these are some interesting observations. So, I stop here today. You solve some interesting problem from Parker Smith's book, a machine connected to bus. This why I have discussed after the Hopkinson test is similar to this only, instead of supply. So, I hope it will enhance your understanding of DC machine, particularly its operation when it is connected to bus, another supply, whether it is running as a motor or generator, things like that. So, that you can decide on your own, yes, under this condition it may supply power to the bus, under other condition it will draw power from the bus, and so on. So, thank you.